Hi everyone, and welcome to today's lesson, which is on graphing linear equations. At this point, you should have already seen the first lesson in this unit, which we did yesterday, and introduced the idea of what a linear equation is a little bit, and then we spent a lot of time talking about slope. If you have not already watched that lesson, make sure you watch that lesson first, because we're going to be using everything we talked about in that last lesson on slope to help us do what we're going to do today, which is graph linear equations. When we talked about and introduced linear equations yesterday, one of the things we said are linear equations are straight lines, and I drew like a very rough picture of a graph and a linear equation, which is that straight line on the graph. Today we're going to learn how you do that. So if I give you information, how you use that information to draw yourself a line. To help us start off, instead of jumping like right into algebra, crazy looking problems, we're going to go back to this word problem and use some of the things you already know. So for this first one, it tells us the temperature outside is -3 degrees and is increasing 2 degrees every hour. At this point in the class, one of the things you already know how to do is take that information and represent it with a word problem. So let's do that now. They're telling us what the temperature is. So my equation could start off, well, the temperature is what? Well, the temperature outside is -3 degrees. That's our starting point. And then it's increasing 2 degrees every hour. Well, I could go ahead and I could say, well, it's starting here at -3 degrees. And it's increasing. I underlined increasing because that means it's going up. It means I'm adding to it. It's going up or increasing 2 degrees every hour. And 2 degrees every hour, lots of times we would go ahead and say 2h, where h represents how many hours have gone by. That's a skill we did in our first unit, specifically in the lesson where we talked about equation word problems. Now, from this information, something that you could also do is you could create yourself a table, right? We could say, well, at hour 0, before any time goes by, what's the temperature? Well, it's still that starting temperature. It's still -3 degrees. So I could say 0, -3. Well, after 1 hour, what's happened after 1 hour? Well, after 1 hour, it's increased 2 degrees. So I'm going to kind of use this over here as just like a thermometer almost. So it started at -3 degrees and it increased 2 degrees after 1 hour. So it went up, boop, boop, it went up to -1 degrees. Well, what about after 2 hours? Well, another hour has gone by, so it's gone up another 2 degrees. What would that next temperature be? Well, if it's gone up 2 more degrees, that would take you to 0 and then to 1. I held up 2 fingers, but 1 degree. And then we could keep going at our third hour. Well, it's gone up another 2 degrees. So if it's gone up another 2, 1, 2, 3, so now it's 3 degrees. And we could keep going with this table. It's nice to have a table though, because what we're doing today is this idea of graphing. Similar to the graphs we were looking at yesterday with slope, you might notice my graph is a little cut off. Do you remember why we said that was yesterday? Why the graph just cuts off right here instead of continually going in that left direction? Well, today we're talking about hours on our x-axis, and you cannot have negative hours, right? We can just move forward from that starting point. So that's part of the reason why the graph looks like this. I can use all this information though to graph on our graph. So on our graph, I would want to show, well, at hour 0, the temperature was -3 degrees. So the temperature was down here. After 1 hour, the temperature was -1 degrees. So I can put a point there. After 2 hours, the temperature was 1 degree. So we could put a point there. And I could keep going, right? 3 hours, the temperature was 3 degrees. You obviously could plot more points if you want to, but notice I've got all these little points here. What I'm trying to do is relate this to linear equations, which remember we had said a moment ago, linear equations are lines, or straight lines on our graphs. So I'm just going to go ahead and connect all these points. Another reason why a line makes sense is we've all experienced temperature, right? It doesn't suddenly just change in a split second, right? It doesn't go from -3 to here -1. In between that starting point in that first hour, the temperature is slowly rising until it's finally rose 2 degrees after 1 hour, another 2 degrees after 1 hour. So this line is showing all those in-between temperatures as well. So this is one example. I've got one other example that's similar to this, and then we're gonna pause and kind of see what does it all mean. The other one, still about temperature. This other one though gives us different numbers this time. This one here is saying the temperature outside decreases 1/2 degree every hour, starting at 4 degrees. Go ahead and do what we did in that first problem. Go ahead and see if you can represent this with an equation. Well, for this one, we've got still our temperature equals. This time they're telling us it's decreasing 1/2 degree. Decreasing means it's going to be negative, and it's decreasing 1/2 degree every hour. So that's where my variable is going to be. It also tells us it's starting at a +4, starting at 4 degrees. So I'll put my +4 there. You could have your 4 at the beginning or at the end. It doesn't really matter as long as that 4 is positive and the 1/2 degree every hour is negative. Now using that information, it's a little scarier because there's a fraction in there. But the idea is the same. Our starting point at hour 0, it was 4 degrees. It is decreasing 1/2 degree every hour. So after 1 hour, if it is decreased 1/2 degree, what would that be? It would be 3.5 degrees. After 2 hours, well, after another hour, it's decreased another 1/2 degree. So that's not as bad. That's 3 degrees. After 3 hours, if it decreases another 1/2 degree, well, now it's down to 2.5 degrees, and we could keep going. There'd be some fractions mixed in with our numbers here. Last part's also the same idea. We could use this information to make us a graph. If I got starting hour 0 at 4 degrees, and then our first hour, we're down here at 3.5. So I'm just putting it between the 3 and the 4. For 2 hours, we're at 3 degrees. For 3 hours, we're at 2.5 degrees. And again, I could draw a line here. What I want to show you is how this is going to relate to all of the stuff we've been doing on slope yesterday and all the stuff we will be doing in this lesson with graphing. So to use this one as an example, but if you also happen to write anything down from that first one, it's another example for you. Notice when we went to graph, where are we starting? Well, we're starting on our y-axis, and I'm starting at this number here, the 4. The 4 was our constant. It didn't have a variable with it. The same thing was true in that last one. In that last problem, we had started at -3. That was the starting temperature, and that's where we started on this y-axis. Well, and what else are we doing? Here, this -1/2 is telling me how much the line is changing. So that negative is telling me my line is going down. Where else have we heard that before? Yesterday, with slope. Remember how we said yesterday, if the slope is negative, it's telling you your line is going down? Look, same idea here. This number here is negative, so our line is going down. It is going down 1/2 degree every hour. It is going down 1/2 degree every hour. Now, if it's going down 1/2 degree every hour, notice it has gone down 1 degree after 2 hours. It has gone down 1 degree after 2 hours. It has gone down 1 degree after 2 hours. Where have we heard that before? Again, with slope. Notice going down 1 over 2. That's describing rise and run, what we did with slope. I use all this to kind of introduce this idea of graphing linear equations. What we're going to do today is very similar. This idea of like starting here at our 4 and then using this number to plot more points on our line is very similar to what we're doing today. What's different about today is the problems I'm going to be giving you aren't going to be talking about temperature. They're not going to have temperature in hours, and you won't be able to relate it back as nicely to a story. Instead, they're going to look something like this. Notice one of the first things that's different is we've got x's and y's in our equations. Linear equations, especially when you're talking about graphing them, you usually have x and y, which goes back to x coordinates and y coordinates, the x-axis and y-axis. It's relating back to that traditional coordinate plane or graph. Some of the other things, though, are still the same. That number that's by itself would be our starting point, and then this other number here with the x is what's telling you the change. Before we get into graphing, I just want to put some vocabulary to everything we've been talking about. These equations here are examples of something we call slope-intercept form. What slope-intercept form looks like is any equation that's written in this form. Y equals mx plus b. If you can compare an equation to this form, if it looks the same, it fits in the same format, m, so the number that's with your x, m is the slope, and then b, that number by itself, is the y-intercept. So that temperature example we had talked about said something, oops, it was an H, not an X, something like this. And remember we had said, notice on the graph I'm starting at 4. 4 is where it was on our y-axis. Well, that's because 4 is the y-intercept. And then that negative 1/2, we were relating a bit to slope. Notice that's our number here with the variable, and that is the slope. So keeping all this floating around in your head a little bit and relating it to some of the stuff you already know, let's go ahead and look at some examples. So this first one is asking us to graph the equation y equals 2/3 x minus 4. Now notice the graph looks different. It's no longer talking about hours, which is why we have the entire x-axis. It's no longer talking about temperature, but the idea is the same. If I compare this equation to slope-intercept form, so if I compare it to y equals mx plus b, there's two things we can learn. We can learn b, which we had said earlier is our y-intercept. I can see b is the number -4. Make sure you include the sign with the number. What that tells me, if my y-intercept is -4, is that when I go to graph my line, I'm going to start at -4 on my y-axis. So I'm going to use this to come to the y, come down here to -4, and that is where my first point begins. I've been asked, why are we using the letters m and b for slope and y-intercept? I have no clue, but something Denise has said is that b means begin here. It doesn't, but it's a helpful trick to remember. This is telling us let's begin at -4. Now the second part of this is we need more points. In order to draw that line, I need more points, but I don't know which way to draw yet. Well, that's what we're going to use our slope for. Our slope m is 2/3. I need to use what we learned yesterday, this idea that slope can be represented as rise over run. That's going to help me plot more points. So if I'll put it over here, if my slope, which I'm going to write as rise over run, is the number 2/3, I can match that fraction up with rise over run, and that's going to tell me exactly what I need to do. Starting at my y-intercept, starting at that beginning point, we need to rise 2 and run 3. So starting here, I want to rise 2, don't put a point yet, rise 2 and run 3, and then put your points. Now in our temperature examples, I had put a lot of points. At a minimum, you need 2 points. Now I can see where the line is, but you can plot more points just to make sure that line goes all the way across the graph. So I could do the same thing again. Now starting here, I can go up 2 and over 3 to get another point. If I tried to keep doing that, it would take me off the graph. But we've got 3 points now. The last part, remember linear equations are lines. I need to graph a line. So I would come in and draw the most beautiful straight line ever going through my graph like that. I'm putting arrows as well to indicate that this line goes on forever. It does not stop just because my graph stops. Just like these arrows here mean the graph goes on forever, same thing is true with the line. So that would be the graph for the linear equation y equals 2/3 x minus 4. There is one other one we're going to do together. We've got graph y equals negative 2x plus 3. What do you think my first step is going to be? Well, similar to over here, I could come and say, well, I'm going to use this form to help me graph. And if I do that, I notice that my y-intercept is positive 3. So my first thing I'm going to do is plot my y-intercept, which is 3, on my y-axis. So I'll come in and I put a point here at 3. Our next thing we did before is we used slope to find more points. So here I can see my slope is what? Well, slope is negative 2. Sometimes people want to say negative 2x. Slope is just a number, no x. Slope, the m, is negative 2. So I can say my slope is negative 2. Well, what did we do with slope last time? Well, we used the formula rise over run to think of slope to help us get more points. So here I could say my rise over run equals, well, what? This isn't a fraction like it is before. Do you know how to make negative 2 look like a fraction? If you want to make anything look like a fraction, put it over 1. So I would say negative 2 over 1. And that helps because just like before, it's telling me what to do. If I start here, how am I going to get to the next point on the graph using this information? Well, my rise is negative 2. Negative means we need to go down. My run is 1, so I need to go over. I'm going to start here and I'm going to go down 2 over 1. And we can keep doing this again and again until we fill up that graph. I can go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. One of the things I didn't show last time, but I'm going to show now, is you can also put points on this side. Just reverse it. Instead of going down 2 over 1, I can go up 2, backwards 1, up 2, backwards 1. And if I do that, up 2, backwards 1, up 2, backwards 1, it gives me even more points on the line. Your line should always be straight. So if at some point you maybe switch numbers around by accident or you start doing something like this, that should be a warning because look, that line is bending. It should never bend. The slope, the direction should be the same the entire way. So that's a good clue that something's off if your line starts drifting a little bit. But I'll put those points back in. And then our last step is to draw that line. If you were looking at this and saying, oh my God, what is she doing? In class, a lot of times if this is new for students, it's really confusing at first. But I promise you, there's going to be a moment where you're like, oh, like it's just counting. It's not bad. I've seen it happen so many times. So if you're at home feeling really confused, trust me, trust the process. You'll get to the point where you're like, oh, okay, I get it. One of the things I will say students make the most mistakes on is the direction, specifically if the line is going up or down. One of the things we talked about in yesterday's lesson on slope is you learned that if the slope is positive, the line should be going up, and if the slope is negative, the line should be going down. Because that's a mistake that a lot of students make when they're first beginning this, I strongly recommend that after you've agreed on what your graph is going to look like, that is a good thing to check. Lots of times students do like the 2 over 1 correctly, but they go the wrong way. Instead of going down 2 over 1, they might go up 2 over 1 and have their line going this direction instead. So checking to make sure that if your slope is negative, the line goes down, and if your slope is positive, the line goes up is going to be a really helpful trick to do. Keeping these examples in mind, we've got 2 for you to try. The first one says this: which graph below shows y equals 2/5 x minus 1? Go ahead and pick a graph. Well, if I was a student for this one, I would use exactly what we just finished talking about with slope telling you the direction to help me eliminate one of these. Notice the slope is positive. That means I want a line going up. This graph here from left to right, that line is going down. That automatically means my answer should not be C. So I'm left with these two. I would then want to check, well, let's see, did they get the y-intercept right? The y-intercept is -1. Let's see this one. Yep, it's at -1. This one here. Yep, it's at -1. So that's not the difference. What about our slope as 2/5? That's rise over run. Should be 2/5. So starting at that point, which graph goes up 2 and over 5? Well, that would be graph B. Goes up 2, 1, 2, and then over 5 there. This graph has got it backwards. This has got a slope of 5/2, which is opposite of what we want. So this is our first one here. The second question, I know that you do not have a graph that you can graph on right now. So instead, just describe for me in words, what would you do to graph the equation y equals -3x? Make sure you don't leave out any steps. Tell me everything. What would you do to graph that equation? All right. Now the last part to this is a lot of these equations were nice because they looked like slope-intercept form. They looked like y equals mx plus b. This one here kind of does. We've got y equals mx plus b, but that plus b was missing. What do you think it is if it's missing? Well, it's 0. So for this one here, your y-intercept would have been 0. The rest of it, though, would have been similar to what we said earlier. Make sure you come back to Edpuzzle, by the way, to check your answers. So that written response, you don't know if it's right or not until Denise or myself, sorry, that's the microphone, until Denise or myself come in and grade it. So you want to make sure you're checking back on those videos you've completed so that you can see our comments we leave you, because we try to leave you nice comments. Speaking of this one not looking exactly like y equals mx plus b, that is the last part of these notes. So not all linear equations are going to look like slope-intercept form. I've got an equation here. If I try to compare it to y equals mx plus b, notice this equation does not begin y equals. The problem with it not being in slope-intercept form is I can't look at this equation and say, ah, yes, the slope is this number. Ah, yes, the y-intercept is this number. We can't just glance at it and get that information. So instead, what we are going to have to do is change it around to look like this equation. Another way to think of that is we need to solve this equation for y. Now, if that is sounding a little familiar to you, it could be from a past algebra class, but it also could be from last week when we talked about literal equations. We spent a lesson talking about how you solve an equation with multiple variables for one particular variable. And part of the reason that skill is so important is for stuff like today. In order for me to graph this, I need to solve for y to help me change it into slope-intercept form. So I've got this equation here. And whoop, that's not going to be helpful. I've got this equation here, and we want to get y all by itself. You have looked at literal equations before. What do you remember? What would we want to do first? Well, I've got a 3 I need to get rid of and a -12x. We always start with that constant, that part that's not with the y, which is the -12x. I can come in here and add 12x to both sides. When I do that, the -12x plus 12x gives me 0. Those cancel out. And we're left with 3y equals, do you remember from literal equations? You cannot add these because this one has an x and this one doesn't. So all I have to do is copy them both down, both terms. There's one last step. If I want y all by itself, I need to get rid of my 3 by dividing both sides by 3. When I do that, my 3's cancel out, which leave me with y equals, which is exactly what we want. Now, the difference today is when we talked about this with literal equations, I was okay with you leaving it as like one big weird fraction. However, when we were talking about linear equations, notice I want it in this form. I don't want one big weird fraction over here. I want two separate terms. So for this problem, we are actually going to divide everything out. Remember, this division line going all the way across means you're dividing everything by 3, even if it's something that doesn't divide by 3. We want to make sure we're dividing both of these terms. So for the first part, 12 divided by 3 gives me 4. And then plus 12x divided by 3. Well, 12 divided by 3 is 4. And then I just copy down the x. This one was nice because all those numbers you could divide by 3. If instead, let's say it looked like this, where you can divide one of them, but you can't divide the other. If you cannot divide it, just leave it as a fraction. Don't just copy down the 2x and ignore the dividing by 3. You need to copy, well, 2 divided by 3, we can't do, but I can write 2 divided by 3. I can write a fraction, 2/3. So we would get 2/3 x, if that had been the numbers. For this problem, though, it's not. So we've got y equals 4 plus 4x. This is enough for us to go ahead and graph it. However, it is still a little different from this. Do you see what's different? Well, in our slope-intercept form, the slope and x, that term always came first. Here it's a little backwards, which is okay, but sometimes for students it's a lot helpful, it's very helpful to go ahead and put it in the same form as this, just so that you know, okay, this is my slope, this is my y-intercept, and you don't mix them up. Once we've got it like this, now we can go ahead and graph. If I'm using what we had talked about before to graph, where would I want to start on this line? Well, my y-intercept is 4, so I could start there, go to my y-axis, say, okay, here's my point at 4. And then my slope is 4. We've learned if your slope is 4, you're going to compare it to rise over run. My slope is 4. That is the same thing as 4 over 1. So that's telling me I want to rise 4 and run 1. So starting at this point, we want to rise 4 and run 1. Rise 4. Uh-oh, I am off the graph. Let me keep doing it anyways. I'm going to go up 1, 2, 3, 4 over 1. But the problem is that's not actually a point on our graph. That's not gonna go over well. Part of the reason I showed you in an earlier example that idea of using your slope in the opposite direction is to help you with situations like this. Notice I can't go up 4 over 1, but I do know that I want my line to go this direction. So instead of going up 4 over 1, I can do the opposite, which would be go down 4, backwards 1. If I do that again, down 4, backwards 1, now I'm getting points that are on that line. Down 4, backwards 1, down 4, can't do it anymore. I like putting this point here just to make sure I'm going in the right direction. If I had gone down 4 over 1 this way and gotten this line, that is a different line. We want to make sure that our line is still going up from left to right since that slope is positive. So that's why it's helpful to know how to get points on both sides of your y-axis. Keeping all of this in mind, we've got 2 left. For this one here, before we go into what the graph is going to look like, there's something we've got to do with this equation first. Go ahead and change this equation into slope-intercept form. Well, there are a lot of different ways you can do this. If I'm trying to solve for y and get y all by itself, the most common thing I see in class is that students move both of these over to this side. So they add x on both sides, which would leave you with 2y plus 8 equals x, and they subtract 8 on both sides, which would give you 2y equals x minus 8. Doesn't matter what order you do those 2 steps in, it's either going to give you x minus 8 or negative 8 plus x, which both mean the same thing. That last step would be dividing by 2, which leaves you with y equals, what did you put down for x divided by 2? Well, remember there's a 1 right there, so it's going to end up being 1/2 x, since you can't divide 1 by 2. Needs to say 1/2 x. 2x is not the same thing. 1/2 x, and then if I divide these, I get -4. We get that as our answer. The other way you could solve this is instead of bringing both of these terms over to this side, you could instead bring the 2y over to this side. If you did that, you would be dividing by a -2, but it would work out to be the same answer. Y equals 1/2 x minus 4. Now that we agree on that equation, what would our graph look like? Go ahead and describe it. Well, for this equation, our y-intercept is -4. So my first point would be there at -4 on my y-axis. Our slope is 1/2. If our slope is 1/2, that means my rise is 1 and my run is 2. I want to start here and go up 1 over 2. Up 1 over 2, again and again. You could also do the opposite. Instead of going up 1 over 2, you could go down 1 backwards 2, down 1 backwards 2, again and again, and you end up with this line. Remember I said the biggest mistake students make, lines going in the wrong direction? So I'm just going to quickly glance and say, yes, my slope is positive. My line is going up. From left to right, the line goes up. We've got one last one for you to try. Erase all of this. The last one looks like this. We've got 2x minus y equals 0. Is it graph number 1 or is it graph number 2? Go ahead and try it. Well, when you solve this equation for y, you end up with y equals 2x. That slope is positive, so if you're checking for that, that makes it nice and easy. This is the graph with the positive slope. This would be our answer. It also has a y-intercept of 0, which is imaginary right there. We can't see it, but it's starting at 0. The slope is 2, which means it's going up 2 over 1. So all of that just to confirm that the answer is the first graph. Thank you so much for watching this video. Please reach out to us if you have any questions about graphing linear equations. Like I said, if this is new for you, you've never learned this or seen this before, it probably is looking a little crazy at first, but I promise you the more practice you get, the more confident you will be. Promise. Thanks so much for watching. Bye.